Okay, Assalamu alaikum. So today's topic is the ratio test and the root test. This is our section 9.6. You will recall we have done a number of tests to check when a series converges or diverges. We have done the nth term test for divergence, the integral test, the P series, the geometric series, alternating series, absolute convergence. So today we will talk about two new tests, the ratio test and the root test. Let's write down what the ratio test is about. So we have a series, summation of an, where the an terms are not equal to 0. None of the terms of the underlying sequence of the series are equal to 0. So the test says, first part, if the limit as n goes to infinity of the n plus 1 term over the nth term, the absolute of this, if it is less than 1, then okay, so if the limit, you take the ratio of succeeding terms of the underlying sequence, not of partial sums. Okay, you take this ratio, absolute, take its limit to infinity. If this limit is less than 1, if the limit exists and is less than 1, then the series converges. I will erase this to write the second part of the test. Okay, the second part of the test says, if that same limit that we saw in part 1, if the limit is bigger than 1, or the limit does not exist, as in it goes off to infinity, then the series, corresponding series diverges, does not converge. And finally, you will be wondering, the only excluded case is when the limit is 1. Okay, so let's write down that part. It is here. So if this limit is 1, then the test is inconclusive. What do we mean by that? Meaning the series could converge, could diverge. The test cannot tell us that if the limit happens to be 1. Okay. I will do the proof of this later, or we might do it in worksheet. But I want you to intuitively understand why this limit is kind of giving you an indication of the convergence. See, think of the nth term test. The nth term test says that if the nth term's limit is not 0, then the series cannot converge. Like the terms are not getting small enough for the whole sum to be finite. Well, similarly here, when the n plus 1 term over the nth term, right? If this is getting smaller than this, then the limit will be less than 1. And that's giving you an indication that the series will converge. But if it's not getting small enough compared to the previous term, if the limit is 1 or even bigger than 1, well, if it's 1, both possibilities are possible. But if it's bigger than 1, certainly the terms are in some sense increasing, and then the series is not going to converge, the sum is going to go on towards infinity. Okay, let's do a couple of examples. I will erase this here. You have this series. The summation of the terms look like 2 to the power n or n factorial. Okay? Let's write down the first few terms of the series. You have an n0, and n factorial is also 1. This is 1. So you get 1 plus 2 over 2. This is also 1 plus 4 over 2 factorial. Sorry, this should have been 1. 2 factorial is this. Plus, let's write down one more term, 8 over 6, right? 3 factorial is 6, and so on. Let's see how the ratio test, or what the ratio test tells us about this series, the convergence of this series. So we set up the limit as n goes to infinity. We take the nth plus 1 term, 2 to the power n plus 1, divided by n plus 1 factorial. We divide by the nth term, 2 to the n over n factorial. This simplifies limit n goes to infinity. We divide it by ratio, so we flip the ratio and multiply. We have n factorial equal to n. And now you can cancel some things. 2 to the n plus 1 cancels with this to give you a 2 at the top. N factorial cancels with this to give you n plus 1 at the bottom. This limit, the top is a constant, bottom goes to infinity. This limit is 0, as you very well know. So what's the conclusion? So by the ratio test, since the limit exists is less than 1, we say